In 2011, nuclear power plants were operating normally, producing clean power for Japan. The power plant builders and designers were convinced that every safety system during an earthquake and tsunami was enough to keep these safe around the public. A tsunami tested them, and while many of the sites were safe, special circumstances led to several cores melting down within 24 hours. In 1986, a Ukraine nuclear power plant was undergoing power outage test. Test engineers were confident that nothing could go wrong and safety systems would save the reactor. Under very special circumstances, the core overheated and exploded. In 1979, nuclear power plants on Three Mile Island were running fine until a pressure relief valve jarred. Without the proper training or sensors, the operators managed to partially melt a core. With these statistics, what did Three Mile Island, Chernobyl, and more recently Fukushima have in common? Today, we will be discussing metallic nuclear fuels and a recent uranium-zirconium binary characterization study. Hi, I'm Matt Cullison. I'm an Oregon State University nuclear engineering PhD student working in the nuclear materials group under Dr. Tianyi Chen's supervision. My life, like many, are closely tied to materials. My parents own a small scrap yard in Yachats on the Oregon coast. After graduating high school, I became a mechanical drafter for a bit before going to Georgia and Mississippi for basic combat training and becoming a carpentry and masonry specialist for the Oregon Army National Guard. I deployed to Kuwait and Baghdad, Iraq on high-priority missions, including working at 2 separate U.S. embassies before coming home and becoming a combat engineer, where I studied and employed explosives, counter-mobility, and route clearance. On the civilian side, I took my hand at carpentry, and I joined a scaffolding company in Eugene where I would work on cars on the side. I came to OSU in 2016 and I got my undergraduate degree in 2019. I had an internship at Pearl Harbor, Hawaii, and operated a small construction business during the summers. I grew up around materials and I was involved with a lot of hands-on work, from turning wrenches, operating heavy equipment, to using C4 to breach doors, cut trees, and dig holes. Nuclear engineering appeals to me because climate change threatens us, and secondly, it's a young science. Going throughout my undergraduate degree, a common theme occurred. Thermal power plants are material limited. Oregon State got 2 new nuclear material professors, and I knew I wanted to join that group. At first, I started as an undergraduate researcher, polishing metallic samples in the basement of Dearborn Hall, learning the craft, digging into metallurgy books, and learning about the material challenges we face as nuclear engineers. I took a seminar a year ago and toured PNNL. We actually saw where the plutonium was made for our weapons program. Large graphite blocks, large steel pipes, an entire river to cool the whole thing down over 600 square miles of land with one of the largest cleanup programs in the entire world. That is when it was cemented in my mind. There's a lot of work to do, and I picked the right major. I finished up my Army contract, and I put my application in for graduate school. I started learning about microscopes, starting from an old optical microscope that used film to take pictures, and worked my way up to working with cutting-edge, multi-million-dollar electron microscopes. Last spring, our group received some nuclear materials from Idaho National Labs for a nuclear fuel texture study figuring out the grain size. We went through difficulties because some of the tools that usually make our tasks straightforward didn't work. Research is difficult because the world is a very imperfect place, and nothing works exactly right. After weeks of analyzing data, communicating with scientists, reading, writing, and editing journal papers, we finally published to Cambridge's open source Journal of Materials Research. I was invited to present at the seminar to give students perspective on nuclear material research going on at Oregon State University. Today, we'll be going over a very healthy metallic fuels introduction, over some tools and methods used, and finally some of the results that we found in this paper. Back to the question at hand. Three Mile Island, Chernobyl, and Fukushima were all nuclear power plants. They all used water, they all had zirconium cladding, they all failed, they all damaged their cores, and more interestingly, they all had ceramic fuels. Nuclear reactors operate in a very unique fashion. We generate volumetric heat that, unlike gas, oil, and coal power plants, cannot be turned off instantly. Uncooled heat raises temperature, and if the temperature goes too high, material starts melting and causing problems. What dictates our heat production? That would be our fission rate density, which is directly proportional to the neutron flux. Reactivity is our acceleration for neutron flux. Also unique to us is our power is adjusted using orders of magnitude, unlike the engines in our cars. On that note, let's think of operating a reactor much like driving a car. They both can harm a lot of people if not done carefully, but overall, they provide a lot of value to society. In this analogy, imagine car kinetic energy will be the fuel stored heat. Our speed is the fuel temperature. Our brakes are negative reactivity insertions. A positive reactivity insertion would be much like our gas pedal. So we fuel our car up, we get on the road, and we bring it up to speed. And we don't want to go too fast because we'll get pulled over, we gotta go in regulations, and most importantly, we gotta be safe. Let's say there's an accident down the road. We'll be wanting to look very far in the future to find it. Let's say it's a stuck relief valve or a 9.0 magnitude earthquake. We apply our brakes, our fuel is energy packed, and behaves more like a bus. The more kinetic energy we have, the farther we have to travel to stop. So we apply our brakes and hopefully there is enough time to avoid the collision. In worst case scenarios, our brakes have failed, and that's why there is a movement towards accident tolerant fuels. However, that is for another discussion. Let's review the thermal behavior of fuels really quickly. As seen in this Oak Ridge National Lab report, uranium dioxide heat capacity is a function of absolute temperature. Heat capacity is the amount of energy it takes to raise or lower a material by 1 Kelvin. As seen here, it takes more and more energy to raise the temperature. However, once we're up in the higher temperatures, it takes more and more energy to lower the temperature as well. This is much like our bus analogy. It's quicker to go from 0 to 10 than it is from 90 to 100, and vice versa. Imagine taking the integral of this and you'll find the specific internal energy for fuel. As seen here, for the specific heat of uranium zirconium is much lower than uranium dioxide. Using metallic fuel instead of ceramic fuel would be much like driving a car rather than a bus. Much less energy, resulting in easier stopping, quicker times, safer, and ultimately more responsive to our inputs. Internal energy is not the only piece of the puzzle. Thermal conductivity is better in metallics compared to ceramics. Low thermal conductivity is the same as being insulating. This is the same reason we use ceramic coffee mugs and metallic tubes for our heat exchangers. Ceramic and metallic fuel have about the same thermal conductivity at room temperature. However, as seen here, at higher temperature, ceramic fuel becomes more insulating, while metallic fuel becomes more conductive. This has a couple implications. Ceramic fuel will have a much higher centerline temperature and greater temperature gradients that induce more residual stress and strain, whereas metallic fuels will become better conductors when they become hotter, which is more desirable in an accident condition. Furthermore, it allows us to run our fuel with greater safety margins due to a lower centerline temperature. Another piece of the thermal behavior is the thermal expansion. Shown here is 2 equations for the thermal expansion between ceramic and metallic fuels. I took the honors and plotted them against each other. 2 things to note. Metallic fuels have a greater expansion rate. However, ceramic fuels have a greater total expansion in higher temperatures. Combined with a lack of thermal conductivity, the fuel experiences significant thermal stress on top of the other stress induced inside the fuel itself. This can cause unwanted pellet cladding interactions discussed later. Ceramic nuclear fuels, such as uranium dioxide, are chosen for their excellent melting temperature that is much higher than metals, and it cannot burn as it is already in the oxidized state. Uranium dioxide is a black solid. It comes to the factory in powder form, where it is mixed with an organic binder, pressed into pellets, and sintered in a furnace, before being pressed into zirconium cladding and assembled into fuel assemblies, ready to ship. Historically, metallic fuels have been investigated from the mid-1940s. Notably, experimental breeder reactor 2 used uranium, plutonium, zirconium ternary fuel. There are 3 main fuels of interest that include the uranium-zirconium binary system, uranium molybdenum system or UMOLY, and uranium silicide. Today, we'll be focused on the uranium-zirconium binary system. So where is the closest location that we can find metallic fuel? Other than our lab, the Triga nuclear reactor uses a uranium-zirconium hydride fuel. The OSU Triga reactor was built in 1967 and is rated for 1.1 megawatt thermal, and Triga gets a lot of credit for its metallic fuel. is shown on DOE's website. Low enriched, long lifetime uranium zirconium hydride fuel is the fundamental feature of the TRIGA family of reactors that accounts for its widely recognized safety, rugged, dependable performance, economy of operation, and its acceptance worldwide. Additionally, the large prompt negative temperature coefficient of reactivity, characteristic of usuric fuel, results in safety margins far above those achieved by any other research reactor fuel. Large reactivity insertions are readily accommodated in routine operation for some applications, and furthermore, inadvertent reactivity insertions have been demonstrated to produce no damage to the TRIGA cores. Power coast down from full power after loss of forced flow cooling and results in power scram have been demonstrated to be very benign event, and the reactor immediately available to return to full power. What does this mean? We can pneumatically shoot a control rod out of the reactor, let it go to full prompt supercritical, and without human input, the fuel becomes subcritical due to its strong negative temperature reactivity coefficient, lowering the power to normal conditions all within milliseconds. Metallic fuel allows us to pull safely, reliably, without damage, and without active safety systems. It makes a spectacular flash of blue light, known as Cherenkov radiation. As mentioned earlier, metallic fuel is used in the experimental breeder reactor too. A breeder reactor simply means it produces more fuel than it uses. Current light water reactors produce some plutonium and account for about a third of the power output. However, a key point is breeders create more fissile fuel than they use. Generally, fast reactors are used for breeding. However, some thermal reactor designs allow for U-233 breeding using thorium-232. Experimental breeder reactor 2 had 67% enriched uranium when fresh. It was alloyed to a 10 weight percent zirconium, and the long fuel rods were inserted into thin stainless steel cladding along with liquid sodium for fuel pellet and cladding gap. 2 impressive metallic fuel safety tests were conducted using this special reactor. Firstly, they shot off the main coolant pump at operating conditions, which was 62.5 megawatts thermal, bypassing normal safety features. The core dropped to a near zero power within 5 minutes due to the negative temperature reactivity coefficient of the fuel, combined with the thermal expansion of liquid metal coolant. The same day, they got it back up to power and shut down the primary pump and blocked the secondary pump. Without anywhere for the heat to go, everything started to heat up. The fuel, coolant, and structure all expanded, and the negative reactivity temperature coefficient made the fuel negatively reactive and therefore stopped the chain reaction, and the reactor shut off passively. Let's discuss more on nuclear fuels in particular. Metallic nuclear fuel also allows for a faster neutron spectrum due to the relatively heavy alloying elements such as zirconium instead of moderating oxygen. The advantages of fast reactors are numerous, including the ability to burn long-lived nuclear waste, breed additional fuel, and has less reactivity loss over the lifetime of the core, which designers can use to extend the core life and improve safety margins. Additionally, it's easier to fabricate. Fuels can be made into creative designs ranging from ingots, slugs, rods, and an annulus. Generally, metallic fuels are long uranium slugs and have a clad with enough room to allow for irradiation swelling, sodium to prevent contact thermal resistance, and a gas plenum at the top of the clad to capture gaseous fission products. An important factor used by metallic fuel enthusiasts is smear density, or the cross-sectional area of the fuel inside the area of the cladding, or sometimes calculated as the ratio of the actual fuel density divided by the theoretical fuel density. However, due to its closeness to 1, it's generally omitted, but in publications it should be noted for clarity. Steady state conditions during normal operation conditions include fission gas release and fuel swelling, because we are fissioning atoms into a slew of other elements. We must consider some of the effects of having a significant portion of the periodic table in our fuel during operation. Elements include solids, liquids, and gases. Sometimes they're soluble into the matrix, and this is desirable because we want a homogeneous fuel. It's hard to think of a solid as soluble, but it is the reality. However, there are some elements that do not like to form chemicals. These are called noble gases. Xenon, krypton, and helium are of major concern. These bubbles can form extremely high pressures on the order of gigapascals. If near the edge of the fuel pin, bubbles will either leak or, under circumstances, explode, sending metallic particles into the fuel cladding. Insoluble gases under extremely high pressures cause mechanical strain. Radiation-induced strain is called fuel swelling. Swelling is actually strong enough to burst fuel cladding, and it is the limiting factor for fuel until advances in optimizing smear density is eliminating swelling failure as being the primary mechanism for fuel failure. One of the major advances was theoretical work that showed once volumetric swelling reached about 30%, the closed pores will connect with one another, forming an open pore microstructure so fission gas can escape into the plenum. The release of gas allows the material to relax and reduce swelling. An optimum smear density of 75% was found to allow swelling in the cladding without much pellet-clad mechanical interaction. The transition from closed to open pore structure is gradual due to the statistical nature of fissioning. Usually this is measured as fission gas release as a function of burnup as shown here. A large plenum works better as it can hold more gas, therefore lowering the cladding pressure. Swelling has been noted as anisotropic or uneven when looking at the rods axially versus radially. Radial swelling is more significant due to the temperature gradients. Additionally, in uranium zirconium alloy, the zirconium redistributes, forming more temperature gradient. Fuel cladding interaction can be broken into two phenomena. This includes fuel cladding mechanical interaction and fuel cladding chemical interaction. Sometimes it's called pellet clad interaction because in ceramic fuel we usually use pellets. Mechanical interaction is just that. Fuel swelling into the cladding, and it causes an extreme amount of stress. However, it can be accommodated by lowering the smear density and just allowing the fuel room to expand as mentioned earlier. The maximum swelling should occur near the cladding to produce minimal stress. You must be especially careful when pushing to a higher fuel burnup. Solid fission products build up in open pores, forming closed pores that may undergo swelling again. In addition, contact with the cladding may close conductive gas paths to the plenum, and the gas will have to push axially to the plenum. One more challenge to consider is that the plenum contains too much gas. Gas bubbles will have less driving force to push to the plenum. In addition, the cladding will experience more stress. However, proper fuel design allows us to sleep at night, knowing that fuel mechanical interaction will not be the first thing that destroys our reactors. Fuel cladding chemical interaction is much more complex. Anytime fuel touches the cladding, you're encouraging fuel to diffuse into the cladding, and cladding to diffuse into your fuel. It is a very complex problem because stainless steel and fuel have so many elements. In UZIRC's case, we have 5 major players, plus sodium gap filler, and the rest of the periodic table is minor players. Uranium, zirconium, iron, nickel, chromium, and sodium have different behaviors. A general guideline is keeping the temperature down to reduce solubility and prevent leaching. One consideration is the formation of eutectic uranium or eutectic plutonium that has an even lower melting temperature. These eutectic formations don't even have to be eutectic. Even getting closer to a eutectic composition can lower the melting temperature. In addition to diffusion of our cladding in the fuel, fission products tend to build up at the fuel-clad interface that are too complex to simulate. Experiments were done with 2 different fuels and 3 different claddings, and cross-sections were taken and studied. Results are reported in Table 2 using different conditions. Pellet-clad interactions ranged from 540 to 600 degrees Celsius, and some zones were up to 170 microns thick, or 0.17 millimeters thick, of diffused material. Burnup also plays a significant role due to the porosity and sheer number of elements present. Highly interactive areas are also believed to be the areas where the cladding will first fail. Constituent redistribution refers to the alloy changing composition during use. A U10 weight% zirconium alloy rod will have a very significant compositional gradient, being uranium heavy near the edges of the rod and zirconium rich near the center of the rod. Because of the strong temperature gradient radially, we generally do not see an axial redistribution. Temperature, time, and burnup all significantly affect the compositional gradient. Compositional gradients affect the local fuel melting temperature and may affect neutronics of the fuel too. Some effects can be desirable, such as zirconium building up near the clad, whereas others, such as lanthanide buildup near the clad, can be less than desirable. Fuel designers must consider all of this. So that's a pretty healthy introduction to metallic fuels. So for the second part of this seminar, I want to get everybody comfortable with some of the tools and the methods that we used in this publication. So first of all, we're going to talk about the scale of things. So the distance between atoms is measured in angstroms, and is generally the smallest distance that we work with. There are 10 angstroms in a nanometer, and in fact, becoming comfortable with the scale of things is important when working with materials. Nanoscale is anything less than a micron, and is generally best observed with a transmission electron microscope, or TEM. While the microscale is anything less than a millimeter, it is best observed with scattering electron microscope. Sometimes mechanical pencil lead is measured in like half a millimeter or 0.3 millimeters. Well, this is actually 500 microns thick or 300 microns thick. This is technically microscale, however, this is considered mesoscale for accurateness and is best observed with an optical microscope. A hair is roughly 15 microns thick, and here we can observe the difference in the resolution between an optical microscope and an electron microscope. And you can see that once you're down to that scale, and while sure you can see it with an optical microscope, it's best left to the scanning electron microscope. So first, we'll discuss optical microscopes. We have all hopefully used optical microscopes in high school or college. A new concept to some, I hope, is bright field and dark field imaging. Bright field uses a central lens light and highlights flat areas that you're looking at, while dark areas are not flat. Dark field uses high angular light as seen here and highlights the imperfections as shown. Electrochemical polishing and etching, sometimes called electropolishing or electroetching, uses accelerated corrosion to preferentially corrode in certain areas. Polishing preferentially corrodes the sample to become more flat, whereas etching preferentially corrodes grain boundaries to reveal them better under a microscope. Also of importance is the removal of any oxidation layer that may have happened during sample storage. Uranium loves to oxidize and has made electron backscatter diffraction impractical. We'll discuss that in a little bit. Let's discuss electron microscopes. As you can see, the top of a particle accelerator, there is a tungsten filament that produces plenty of electrons and then accelerates them across the voltage, generally 2000 to 30,000 volts. Because they are charged particles, we can use magnetic fields to focus the electrons to a very fine area. Electrons have a much higher resolution due to the shorter wavelength than light. So when you're looking at an electron micrograph, electrons are smashing into the sample, exciting secondary electrons that are collected and used to produce an image. Primary electrons sometimes backscatter off of an atom and can be used to produce an image as well. In images, more energetic electrons will penetrate deeper into the sample, revealing what is below, while low energy electrons are used to get very fine details from just the surface. Light contrast spots on the image are heavier elements, while lighter spots are lighter elements. So for this study, the darker spots will be zirconium, and the lighter spots will be uranium. Let's talk about energy dispersive X-ray spectroscopy, called EDS or sometimes EDX. It's preferential. You can say what you want. Excited secondary electrons leaving the atom produce a hole in the electron shell. The hole is filled by a higher energy electron. The excess energy produces characteristic photons called X-rays. X-rays are collected with some efficiency. They are binned according to energy. The resulting graph is what we call a spectrum, or a spectra for plural. The peaks are associated to electron energy bands. Spectrum patterns are then related to a library of spectra to determine the elements present. Elements are then weighted and an elemental composition can be found. A single spectra is called a point scan. Multiple points can be put together to create line scans or an area scans at the expense of time and or accuracy. Area scans are very useful tools and are often used to produce compositional maps to further describe microstructure. You'll see this more and more as you go on through the term. Each element will be represented by a specific color. The longer the scan was taken for, the image will be more complete, accurate, and useful. Let's talk about X-ray diffraction, or XRD. X-rays have been very useful for science in recent history. They're high enough energy that their wavelength interact with the very distant between atoms, or angstroms, and powerful enough to penetrate most matter. The lack of charge, unlike electrons, allow them to go unaffected. Atoms and metals are aligned in a crystal lattice. To make measurements on the crystal lattice, such as interatomic distance, we can shoot X-rays at an angle, and depending on the angle, we may find reflective X-rays to be in phase. This is good evidence that we're on the right scale. We can relate the angle, phase, and wavelength using Bragg's law to determine the interatomic distance between planes, giving us an idea on what materials we're looking at, specifically the crystal structure of the solid. With the structure, we can determine the phase's name and provide useful insights to material behaviors. Let's discuss electron backscatter diffraction, or EBSD. Much like XRD, electron diffraction can be used to determine crystal orientation. Very useful information come from EBSD maps such as crystal misorientation, grain size distribution, anisotropy, and a plethora of other interesting pieces of information. However, due to the strong tendency for uranium to oxidize, electrons will interact with the fine oxidation layer. This is problematic because we want to find the information from the sample in the metallic structure, not the oxide layer. A little deeper into the science of how this works is electrons scatter off the crystal lattice. Because of the symmetry of the beam, the reflected electrons will come off as cones. Cones are projected into a detector and they form what we call Kikuchi bands. The bands are related to a library of Kikuchi patterns and data can be extracted, such as tilt and roll of the grains. And finally, let's discuss machine learning. Machine learning is teaching a computer what a certain feature is. In our case, we taught a computer what a precipitate looks like under a micrograph. And then we allowed our computer to recognize all the other ones to make a map with that information. If it's wrong, we tell it it's wrong, vice versa. Machine learning can be very complex, or in this example, very simple. Now that we got a brief introduction and some of the methods that we used, now we can talk about this publication's results. So Idaho National Labs manufactured the samples and annealed them before sending them to us. Due to the uranium content, we could not just simply mechanically polish them, so we turned to electropolishing. Because the American Standard of Testing Material Methods recommended using perchloric acid that runs the danger of an explosion, we had to come up with a new method to electropolish the samples. We used Kelly's recommendations and used phosphoric acid. However, we ran into a lot of pitting and undesirable behavior. We adjusted it using a lower in temperature and lowering the reaction rate, and played the voltage until we got desirable results. Eventually, we preserved the fine precipitates that are really valuable to characterize this two-phase structure. We use XRD to find the crystal structure of the material. Obviously, there's two phases, so we characterize the precipitates and then the matrix of the structure. And found the matrix was a mix of delta and gamma phase uranium zirconium alloy, while the precipitates were alpha phase uranium. The electron micrographs revealed that a dendritic structure or tree-like structure in the matrix. Annealing for 1 hour at 650 degrees Celsius revealed that there was fine precipitates, but after annealing for 24 hours, the precipitates coarsened and the dendritic microstructure disappeared. Machine learning determined that the area fraction of the precipitates was roughly 10 to 14%, It's important to understand that relating area fraction to volume fraction is not possible. Even assuming perfect spheres can show a large uncertainty. The important information we did find was that uranium travels to the grain boundaries, which may have implications for fuel behavior, such as fission gas retention, material strength, and thermal conductivity. This work may support fuel performance codes, manufacturing, and core design. EDS was used to investigate the elemental compositions. Across precipitates, we were observing a supersaturation of zirconium. We were observing an 8% zirconium content, and while this was in agreement with other papers, it was in disagreement with a binary phase diagram suggesting that uranium should only be 0.5 weight percent zirconium. Our co-author told us to check again. So we did. We checked again and again, and finally we found a place that showed agreement. We found a large vein of uranium on a grain boundary, and because we had controversial data, we needed to determine why we were finding different results. It turns out EDS has varying penetration depth depending on electron energy and material. I found an electron excitation volume simulator that was produced by the same person that wrote the software for the electron microscopes. I also read their book and found out EDS can produce X-rays from a pretty high volume, especially in zirconium. Even when an X-ray is produced, it can be self-shielded, especially if it has to go through uranium precipitate or it is really deep in the sample. Additionally, X-rays can be absorbed in the material. Furthermore, stronger uranium X-rays can excite weaker zirconium X-rays, and this is what they call fluorescence. These effects are summarized in the acronym ZAF, or Z-effect, absorbance, and fluorescence. Luckily, the software already accounts for this, and it is very important to tell the machine exactly what you think you're looking at so you can adjust it accordingly. EDS was further calibrated using a variety of standards, including uranium, and was checked using a pyrite standard to be within plus or minus 1.5 absolute maximum. In conclusion, we have reviewed a healthy metallic fuels introduction, some of the tools used in this publication, and our publication's results. If you have any